Today we are going to discuss Ampere Circuital law, its derivations and its applications. We'll apply Ampere Circuital law to different cases there. We'll use it to find magnetic field due to a straight current carrying conductor of infinite length, then magnetic field due to a long solenoid, also magnetic field due to a toroid, and magnetic field due to a thick current carrying conductor at different points. Now we'll also discuss what is the importance of Ampere Circuital law over Biot-Savart's law. Ampere Circuital law statement is the line integral of magnetic field over a closed loop is mu naught times net current enclosed by the loop. Mathematically, we express it as B dot dl equal integrated over closed loop or integration over the closed loop. This is mu naught times I. I will represent net current enclosed by the loop. Now remember one thing, Ampere Circuital law is being used for a closed loop. Second thing, this is the line integral of magnetic field over closed loop, and that is your mu naught times the net current enclosed by the loop. Whereas if you just see Gauss theorem of electrostatics, there we have said that the surface integral of electric field over a closed surface, and that is your 1 by epsilon naught times the net charge enclosed by the surface. So the difference is there. This is for line integral of magnetic field. That was surface integral of electric field. It was E dot ds over closed surface, that is Qi by epsilon naught. So this is for closed loop. This was for closed surface, because this is dl is this elementary length we are taking. So obviously it will be integration over a closed loop, and this is for current and this is net charge there. So be very careful when you are writing the statement of Ampere Circuital law. Now let's see how we apply that. Suppose you have a wire which is carrying out current I1 and it is out of the plane. We take one closed loop like this. This is suppose your L1. So if you take this B dot dl integration over the closed loop L1, this will be mu naught I1. If I take outward direction of the current as positive, we can take it as plus I1. But suppose I have another current I2, and this is, say it is going into the plane, and our closed loop is, suppose this is L2. So for L2, if I take this B dot dl integration over L2, this is mu naught I1 minus I2, because I1 is out of the plane, I2 is going into the plane. Or if suppose I have another current I3 coming out of the plane, and this is the loop L3. So in that case, integration of B dot dl over L3, this is mu naught I1 minus I2 plus I3. So this will be used for different closed loops. We have to just see what is the net current enclosed by the loop. Now let's take the proof of Ampere Circuital law. What we are taking, we have suppose the current I which is coming out of the plane, and this is a closed loop which is enclosing this current. Now we take different elements. Say we take a particular point here where the magnetic field is B1. This is at a distance R1 from this current. And we take an elementary length dl1. Similarly, for the other point which is just close to it at a distance R2, suppose the magnetic field there is B2. and the elementary length we are taking it as dl2. That way we can take the different points where magnetic field values will be different because they are at different separation from this current carrying conductor. And magnetic field at different points from a current carrying conductor, this will be given as mu naught I by 2 pi r, where r will represent the separation from the current carrying conductor. This is for a straight wire which is carrying current I, and we take magnetic field at a distance r from it. So here, if you consider B dot dl1 plus B dot dl2 plus B dot dl3 and so on, if you just go on adding all these, we will get B dot dl integrated over the closed loop. So what we'll get here? B1 dl1, because the B1 will be acting tangentially at that point, or the length which we are taking, which we are moving in that direction, which is a very elementary length. This is suppose dl1, dl2 and other. They will also be in the same direction of the magnetic field at that point. So their angle is 0. So it is just B1 dl1 because it is cos 0 there. Second is your B2 dl2, B3 dl3 and other, because correspondingly the angle between magnetic field and dl value which we are taking, it will be 0 at that point. So this is now magnetic field at a distance r1, which we have taken as B1. So this is your mu naught I by 2 pi r1 dl1. Similarly, it is mu naught I by 2 pi r2 and so on. So if you just continue this one, now we can take mu naught I by 2 pi common, then it will be dl1 by r1, dl2 by r2, dl3 by r3. And what is this dl1 by r1? This will be the elementary angle made at the center, because this is just like a small arc, and r which we are taking it as the distance. So it is the arc by radius. So this will give you the small angle, say d theta 1, d theta 2 and so on. If you go for all such elements which are making the angle at the center, total angle about a point by the entire loop, that will be equals to 2 pi. So it is your mu naught I by 2 pi multiplied by the total angle 2 pi, that will ultimately give you mu naught I. So the expression for Ampere Circuital law, which is your B dot dl, this is equals to mu naught I that we have proved. So this is the derivation of Ampere Circuital law. Of course, you can derive it for a circular loop about a current carrying conductor. But that is not a general derivation. That is a specific derivation for a special case, when you have taken the loop as a circular one. And this is the general derivation that is for a loop of any shape. That will indicate that Ampere Circuital law is applicable for any closed loop of any shape. Let's now do applications of Ampere Circuital law. First application we are taking to find magnetic field due to a straight conductor of infinite length at some distance from it. So suppose we take I is the current whose magnetic field we want to find at a distance d from it. The wire is, or the conductor is kept perpendicular to the plane of the board, and this is carrying current out of the plane. So in this case, if you consider, we'll take an Amperian loop. We'll take circular Amperian loop. So this is the circular Amperian loop of radius equal to the distance where we want to find magnetic field. And its center is at the position of the wire, which is carrying current. So now if you apply Ampere Circuital law, B dot dl, this is your mu naught I. So this we can take as B dl. Now you see magnetic field if the wire is carrying current out of the plane, then magnetic field is circular. And for this case, it will be going in the anti-clockwise direction. Because if you apply right hand thumb rule, which is indicating that if the current is represented by the direction of the thumb, then the curled finger's direction will indicate the direction of magnetic field. So in this case, magnetic field will be in the anti-clockwise direction. So at all point, it is in the tangential direction there. DL is also in the same direction of the magnetic field. So angle between the two is 0. So this case will give B dl cos 0 integral over closed loop. This is mu naught and the current enclosed is capital I. So this is B. And now the length of the entire loop, this is your 2 pi d. This is mu naught I. So B will be equals to mu naught I by 2 pi d. So this is the direction of magnitude of magnetic field, which is mu naught I by 2 pi. For this case, as I told you, the direction you can find by right hand thumb rule. This says that we can assume as if we are holding the wire which is carrying current. And the direction of the current should be same as the direction of the thumb. Then the curled fingers will indicate the direction of the magnetic field. So in this case, if you consider current coming out of the plane, so it is represented by the thumb, the curled finger is indicating anti-clockwise direction. So here, the magnetic field will be anti-clockwise. So if current is out of the plane, for this case, then magnetic field will be in the anti-clockwise direction. Magnetic field will be in anti-clockwise direction. But if you consider the second case, if current is into the plane, that means we represent the direction of current as into the plane, then the magnetic field, this time we'll keep our hand like this so that the thumb is indicating direction into the plane and the curled finger now it is in the clockwise direction. So this will indicate magnetic field is clockwise. So this will give the direction, because remember magnetic field is a vector quantity. So it's not only sufficient to give the magnitude, but you will have to also mention its direction. Now let's take the second application to find magnetic field due to a long solenoid of infinite length. So suppose we have a solenoid which is carrying current I. It is of infinite length. We have shown it by the dotted line indicating that it is going up to infinity. And it has small n number of turns per unit length. So to apply Ampere Circuital law, we need a closed loop. So we'll take an Amperian loop ABCD. This AB we have taken of length L. And suppose the magnetic field due to the solenoid is B. Now this one, just you can think in this way, if you are taking a solenoid, it has large number of turns. And if the current is flowing, suppose in this direction, if we cut the solenoid into two parts along its length, in that case you'll find that if the current is moving like this, you can show the direction of current coming out of the plane and it is going into the plane. If I show the direction of the current like this, so through the upper point it is coming out and at the lower point it is going into the plane. So that is what we have shown by the dots and the cross here. Dot is indicating current is coming out, dot and cross is indicating that the current is going into the plane of this board. So now if you apply Ampere Circuital law to a closed loop A, B, C, D, A. So B dot dl, this is mu naught I. This is the expression for the Ampere Circuital law. And we can write this as B dot dl A to B integral, B dot dl for B to C for this part, B dot dl for C to D, this movement, and B dot dl for D to A. So it is now for the entire closed loop. This will be equal to mu naught I. So this is equals to mu naught. And now the current enclosed, total current enclosed. If I have taken N as the number of turns per unit length, I is the current. In that case, over a length L, the number of turns involved will be your N into L. And if the current is I through each turn, then in that case it is NL into I as the total current enclosed by the loop. So now let's take for the left hand side terms. B is from left to right. We are also moving from A to B in the same direction of magnetic field. So the angle between the two is 0 degree. So it is your B dl cos 0 if you move from A to B. But for B dot dl, when it is from B to C, magnetic field is in this direction. We are moving in this direction, B to C. So the angle is 90 there. So if that angle is 90, then it is your B dl cos pi by 2 integral from B to C. Let's take the third term. It is for C to D. And here, this is the point where the magnetic field we are taking out of the solenoid. Magnetic field out of the solenoid or outside solenoid is 0. So this term will be 0. And this is your B dl cos 3 pi by 2. So this is for D to A. Now why we are taking 3 pi by 2? If B is from left to right, for this case, we are moving from B to C and the angle we have taken 90 degree. That means we have measured angle in the anti-clockwise direction. So if I take for this case, B direction is this. We are moving in this direction. So this is the angle measured in anti-clockwise direction. And if this is the angle measured, then this will be your 3 pi by 2. Of course, these two, whether you take cos pi by 2 or cos 3 pi by 2, both will be 0. So this is your mu naught NL I. Here, of course, for the third one, you can write third term is 0 as magnetic field outside the solenoid is 0. So since it is 0 outside, so this term is 0. And now what we can write? It is BL, A to B, length we have taken as L. Second term is 0 because cos 90 is 0, this is 0. So it is your mu naught NLI, or B will be equals to mu naught NI. L term will get cancelled. So this is the magnetic field due to a long solenoid. If you want to find magnetic field at one end of the solenoid, so suppose you have solenoid which is extending up to infinity. This is the solenoid, suppose. And both direction it is extending up to infinity. I want magnetic field at one end of it. So suppose if I assume that it is divided or it is cut into 2 equal half, this is the point. So that means if I take this point, neglect this one, that means this is the point at one end of a long solenoid extending up to infinity. Or it can be taken for this one also. So magnetic field at one end, if you take, suppose due to magnet left part or right part, magnetic field if I take, it is your B1, or due to this it is your B2. What we are taking as B1 and B2? B1 is suppose magnetic field due to the part which is on right side, extending up to infinity. Or it is, say, it is your B1 extending up to infinity. B2 is magnetic field due to the part which is extending up to infinity on left side. So at this particular point, both will have the direction in the same direction. Because if you take the direction of the current, suppose it is coming out of the plane and it is going into the plane here in this direction, magnetic field is from left to right. So in this case, B1 plus B2, this will give you the total magnetic field. B1 will be magnetic field due to the part extending up to infinity on right side, and B2 is for the part extending on the left side. B1 and B2 both are equal. So what you will get? You will get 2 times B1 equals to B. This is magnitude wise. And that will indicate B1 as B by 2. This is your mu naught Ni by 2. And direction, you can indicate that it is towards right in this case or towards left. So magnitude wise, if you consider, this will be your mu naught Ni by 2. It means magnetic field due to a long solenoid extending up to infinity, this is mu naught Ni, and magnetic field at one end of the long solenoid will be mu naught Ni by 2. Let's take third application. To find magnetic field due to a toroid. Toroid we take like you have a solenoid, you are bending it in the shape of a circle. So if you have a long solenoid, you are bending it in the shape of a circle, it will take the shape of a toroid. It will be called as the toroid. So suppose if I assume that capital N represents number of turns of the toroid, total number of turns, and it is carrying current I. So here, if you take that we want to find magnetic field due to this one, inside this toroid, and the distance we are taking it as R. So R is representing the radius of the Amperian loop which we have considered to find magnetic field. So again, by Ampere Circuital law, you will take B dot dl equals to mu naught I. So this is your B dl cos 0, because again magnetic field and direction of movement there, that will be in the same direction. So in that case it will be 0 at all points, so it is cos 0, and it is integration over the entire loop. Capital N we have taken as the total number of turns, so in that case it is your mu naught Ni, or it is your B into 2 pi R. This is your mu naught Ni, or B is equals to mu naught N by 2 pi R into I. So this is the expression for magnetic field inside a toroid. Now this capital N by 2 pi R, this is the total number of turns, this is the entire length there. So in that case, this can also be taken as number of turns per unit length of the toroid. So this can be written as your mu naught Ni, where N is representing number of turns per unit length of the toroid, which is capital N by 2 pi R. So this will also give you the expression for magnetic field due to a toroid. Suppose we want to find magnetic field due to a thick current carrying conductor. So for that, let's assume that I is the current through a thick conductor whose radius is given as capital R. So it is the thick conductor, like this one, we have taken its radius as R. capital R. And we want to find its magnetic field at different points from this conductor. So suppose we want to find magnetic field at a distance R from it. So taking this R as the radius, we'll construct a circular Amperian loop. We'll have the different cases for this R, whether R is greater than capital R, or it is equal to capital R, or it is less than capital R. So we'll take all those cases. So for this case, we have shown that it is greater than R. So by Ampere Circuital law, B dot dl, which is mu naught I, we can write it as your B dl cos 0 integral over closed loop. This is your, this time, if I take case 1, if small r is greater than capital R, then it will be equals to B into 2 pi r, that is the length of this loop. This is your mu naught I, because I we have taken as the current enclosed by this loop, and I, capital I, is the current flowing through this conductor. So it is capital I, or this is B equals to mu naught I by 2 pi r. This is the expression for magnetic field. Let's take case 2. If small r is equals to capital R, then what will happen? This time it is B into 2 pi capital R, which is your mu naught I, or B is equals to mu naught I by 2 pi capital R. This is for the second case. Now let's take third case. If small r is less than capital R. So for this case, suppose I assume that this is capital R radius of the thick conductor, which is carrying current I, and this current is distributed uniformly over the entire cross section of the conductor. So now this time we'll take a Amperian loop of radius small r, and small r is now less than capital R. So this one will be here, and now this is the section which is enclosed by the Amperian loop. So we will have to consider the current flowing through this part only. Let it be I dash. So what we'll take here? Again, B into 2 pi r as it is. But this time it is your mu naught I dash. I dash is the current enclosed by this elementary section here. That means Amperian loop of radius r, and we'll see how much current is in that particular loop. So this is your B into 2 pi r. This is mu naught. If I assume that the current is distributed uniformly over the cross section, if you take direct current, it will flow through entire cross section. So in that case, it is your mu naught by pi capital R square multiplied by pi small r square. Current per unit cross sectional area multiplied by area enclosed. So this is your B mu naught I r by 2 pi capital R square. Because this pi will get cancelled, it is your mu naught I into R divided by 2 pi R square. So this is the expression for magnetic field when R is less than capital R, and B here is proportional to R. Okay. This indicates that B is proportional to R. Now for this case, if you want to plot the nature of variation of magnetic field with distance, so for that you will get the graph like this. On x-axis you have the distance r, on y-axis we have shown magnetic field, and this is the point which is indicating capital R, that is the radius of this thick conductor. So up to capital R, magnetic field will vary directly to distance. So B is directly proportional to R up to capital R. And after that, it varies inversely to the distance. So B will be inversely proportional to R. And at B, R equals to capital R, magnetic field value will be this much, mu naught I by 2 pi R. So this is the nature of variation of magnetic field with distance for a thick conductor which is carrying current. This is all of Ampere Circuital law and its application to the different cases. Advantage of the Ampere Circuital law is that with little calculation or with simple calculation, you can get magnetic field due to different cases there. You can get the magnetic field for all these cases if you apply Biot-Savart's law also. But then your calculation will be very lengthy.